Okay, no more questions, guys. No? Homework was easy?
Once I figured out that I had to use technology to get a p-value, everything else was not too terribly bad. The question itself, I'm going to go back and almost rewrite it, because it tells you that sample 30 video games, but the claim was about the amount of violence was being done. So you literally were thinking that it's something to do with time, and you find out that your degrees of freedom is 29 and not the difference in seconds.
Oh, okay.
It's like, so, because it's the sample of the video games, this is just the time this thing is being done, you're just like,
So you're trying to find a mean value, and that value happens to be time. Okay, good. Any other questions or comments for yourself? No? Okay. So let's proceed. We've been talking about confidence interval, we've been talking about hypothesis testing. And hypothesis testing, recall, you have some claim regarding the whole population. And you try to make a conclusion for the claim based on an observation involving one or more samples. So far we've talked about two varieties of hypothesis testing. And the varieties depend on what measurement is involved in the claim. So one instance that we've talked about is if the measurement has to do with the proportion of success for the population. And another type of claim that we talked about is a mean for the population. And in both cases, the overall structure of hypothesis testing has been exactly the same. Remember, step one, let's identify the null hypothesis, the alternative hypothesis, assume that HO is true, draw the underlying distribution, identifying the tails, and then the last step was incorporate the observation and decide whether the observation is inside the body or the tail. And then once we decide whether it's in the body or the tail, if it's in the body, that means it's consistent with the distribution, in which case you phrase the conclusion one way, which is fail to reject HO. And if the observation is inside the tail, you phrase the conclusion another way, which is reject HO. Okay, good. And then ultimately, you always want to bring the conclusion back to the original claim. So you phrase it in terms of HO, and then H1, and whichever the claim is, you phrase it with either HO or H1. So that was the general structure of hypothesis testing, and that's been the same no matter what measurement we're dealing with. And we've talked about these two measurements so far. And the only difference between the measurements is that the underlying distribution might be different. Like, for example, with the case of P, population proportion success, we're dealing with an underlying distribution that is a binomial distribution that you can fit with a bell curve. And that's why we've been seeing a bell curve when the measurement has been P. And then because you're dealing with a bell curve, you have where the tail starts, that's defined by a critical statistic that in this case, because you have a bell curve, you're gonna have a critical z-score. And then the observation will have its own z-score, which will be z-test. The critical statistic will always come from a table. In this case, the z-score table. The test statistic will always come from a formula. In this case, the formula is, we said that in this case you have two formulas that ultimately give the same result. So the Book's formula,
P hat minus P divided by the square root of PQ over number.
okay, good. So this is the Book's formula, and then we also said there was another formula that seemingly looks different, but also you actually get exactly the same answer. That was it.
NP, and I kept saying, your mean, because that's what they turn into.
So this is actually the mean.
And then divided by sigma, or the square root of NPQ.
Excellent.
Which
Okay.
is only for when you have identified it as a binomial probability.
Right. Exactly. So this is only true, both of these, when the underlying distribution is a binomial probability distribution. which can be fitted with a bell curve. And you know that's true because the variable involved here is P, a proportion of success. So you can always logically equivalently say a proportion of success is a number of successes out of another number of trials. And because this is your variable, the probabilities that your variable takes on a number of successes out of another number of trials, those are all binomial probabilities using the binomial probability formula, n choose x, and so forth. So because all these probabilities are binomial, the whole distribution is a binomial probability distribution, where the mean is NP, standard deviation is square root of NPK. Okay, good. So that's review when the measurement involved in the claim is a population proportion of success. When the measurement involved is population mean, the difference is the underlying distribution will end up being a t-distribution because your variable here has to do with a sample mean. So for each sample mean, you're looking at how frequently or what the probability is that it occurs. And then the important thing is, if it was just the sample mean, a distribution of sample means would be a bell curve. But that's only in the case where sigma is known. But to know sigma or a population measurement in real life is actually not feasible. So this is a distribution of sample means when sigma is unknown, and you only know the sample characteristics. And so when you have a distribution of this type of variable, this is a t-distribution. And the mean of this t-distribution ends up converging to this actual population mean here that you're trying to estimate. So the difference is that these two distributions are different. They have a different shape. One's a bell curve, one's a t-distribution. And then the only other difference is when you're deciding whether an observation is in the body or the tail, instead of comparing z-score to z-score, you would compare t-score to t-score. So the observation will have its own t-score. Instead of z-test, it's called t-test. And where the tail starts, it'll have its own critical statistic. Instead of z-critical, it would be called t-critical. And just like before, any critical value will come from a chart or a table, and any test statistic will come from a formula. So the formula for this test statistic will end up being so the sample mean you observe minus the true mean that you assume is true from the null hypothesis, and then divide by the quantity S, the sample standard deviation, divided by this variable. So between these two varieties of hypothesis testing, the only difference is the underlying distribution and also how you calculate the test statistic, which formula you use, and how you find the critical statistic or what table you use. But once you get these two quantities, all you do is compare them to see whether the observation is in the body or the tail, and once you determine that, you reach the proper set of conclusions. Any questions? Okay, so today we'll talk about another measurement that could be involved in the claim of a hypothesis test. And that has to do with the measure of variation. So that'll be either standard deviation or variance. You guys knew that was coming? Okay, good, very good. So this should ring some bells from when we were doing confidence intervals for this type of variable, measuring a standard deviation or variation or variance. And remember, when we were doing confidence intervals, the underlying distribution was a chi-square distribution. So And recall that a chi-square distribution, the underlying distribution, looked like this. And then, so every distribution has a body and tails. So whatever the confidence level is will correspond to the body. And then the tails, whether it's one or two tail, in this case I've drawn it as two tails, but depending on H1, it could be one tail. So the tails will be separated by critical values. So one will be, so both will be critical chi-square values. But if you happen to have two tails and two chi-square critical values, you could differentiate between them as one is chi-square left, one is chi-square right. Okay, so that was a throwback, a summary of when we talked about chi-square distributions in the context of confidence intervals. So now we'll talk about this in the context of hypothesis testing that involves a claim that has this measurement, either standard deviation or variance. So let's put this in the context of an example. So before, when we've seen this in the past, hypothesis testing, usually we start with some claim or idea, and then we go to form an observation to try to make a conclusion about that claim for the population. But it doesn't have to be start with a claim and then go to gather your observation as the second step, as long as you have both things. So sometimes in real life, people start with the observation first. They happen to observe things that inspire some idea. And then that idea that it's inspired becomes the claim. So the point is, you could start with the observation first, and then generate the claim, or vice versa. So let's say in this case, you happen to have an observation. Let's go back to the example of, let's say that you're head of quality control at an electronics company, and your job is to inspect gadgets with a specific specification. So let's say that the specification there's this output voltage for each device that you're looking at that needs to be 12 volts. And of course, not every device will be exactly 12 volts. There's going to be some variation around that. So let's say that you inspect 40 devices. And let's say one is 11.96, one is 12.05, one is 11.98, and so forth. So you have all these voltages that are around the true specified voltage of 12 volts. And so let's say that you happen to observe these 40 devices and you enter the 40 output voltages into your calculator, and your calculator tells you the sample mean and the sample standard deviation. So let's say that the sample standard deviation happens to be 0.06 volts. So remember, the sample standard deviation tells you approximately the average distance of all these numbers around its mean. So the average distance approximately is 0.06 volts. So this turns out to be a pretty good standard deviation. So the smaller the number, the less variation of these numbers around their mean. So this is a pretty good standard deviation, but this is only for the sample of 40 devices. So what you really care about is the standard deviation for the entire factory of devices where these 40 devices came from. So based on this sample standard deviation for the 40 devices, let's say that this inspires the hunch that maybe the standard deviation for all devices from the factory is some number that's less than 0.1. Because the sample standard deviation was less than 0.1, so maybe the standard deviation for the whole factory is also less than 0.1. So that's your claim. So the population standard deviation, we're gonna notate as sigma, which is population standard deviation. Remember, a claim always has to do with population measurement. So the standard deviation, let's say, is less than 0.1 volts. So let's go ahead and include 0.1 as well. Let's do less than or equal to 0.1. So that'll be our claim. So this is our claim for the whole population of devices. So now we want to use this observation to make a conclusion about that whole population. So we're going to use the formal substance hypothesis testing, where the only difference will be when we get to that step where we assume HO is true and we draw this distribution, then this distribution will be a chi-square distribution. And that will be the only difference. But all the other steps as a whole will be the same. And so we'll highlight this difference when we get to it. So let's review. What's the first step of hypothesis testing?
Make your null hypothesis and your counterclaim. So.
Okay, good. So identify the two statements, null hypothesis and the alternative hypothesis. So in order to identify those two statements, we have to construct two statements where we only started out with one. So the other statement will be the opposite statement, or the counterclaim.
Sigma is greater than 0.1.
Okay, good. So the counterclaim will be sigma is strictly greater than 0.1. So typically, these statements will usually be in English, in words, but now we were able to start with the statement being in mathematical notation already. So once we have it in mathematical notation, then we pick the statement that has the equality sign, and that'll be the null hypothesis. So which of these two statements has equality?
The claim.
Yeah, the claim. So the claim contains equality. It also contains other stuff like this less than, but it contains equality. So that will be your null hypothesis. So the reason we pick the statement that has equality as the null hypothesis is that equals means that it equals to some number. And so if it equals an exact number, then we can build a model around that specific number. So the null hypothesis traditionally is the statement that has only the equal sign. So if you're asked specifically to identify just the null hypothesis, then start with this full statement and then just take everything away except for the equal sign. So this will end up being sigma equals 0.1 volts. So that'll be the null hypothesis. And then the other statement that remains will automatically be H1, the alternative hypothesis. Okay, so that was step one of hypothesis testing. So step two is we want to assume that HO is true. And assuming HO is true in this case means that we're assuming what is true.
That the standard deviation for all the electronics in the factory is going to be equal to 0.1 volts.
Okay, very good. So assuming HO is true is assuming that this sigma really does equal 0.1 volts. Yeah.
What's the confidence level of the certificate?
Okay, good question. So that needs to be given to you. So let's say that the confidence level is, let's say 95%. So that'll be given. Okay, so within step 2 now, let's say that we draw a distribution. So this distribution that we draw will have a body and it'll have tails. Before, I just drew it generically with 2 tails. But let's draw specifically for this problem. Should this be a 1-tail or a 2-tail test? Okay, very good. So you always look at H1, and then you look at the number of inequalities in H1. There's only 1 inequality, so it's a 1-tail test. So not only is it a 1-tail, but is it a left tail or right tail?
Right.
Right tail, very good. So you look at the variable is greater than the number, so greater is to the right on the number line. You could also draw an arrow where the pointer is. So that'll be right tail, so that we can redraw this so that it only has 1 tail. Okay, so we only have 1 tail and right tail. So the area of the body will equal the confidence level, that's 95%. And the area of all the tails combined will add up to whatever's left over, which is alpha. So in this case, what's alpha or what's left over from 95%?
0.05.
Yeah, 0.05 with 5%. So the total area of the tails will add up to alpha. Since there's only 1 tail here, that full tail will be the amount of alpha, which is 0.05. Any questions? All right. So once we properly identified the areas of the body and the tail, now we're ready to incorporate step 3, which is to incorporate the observation in. So step 3 is to ask ourselves, is the observation consistent with the idea that HO is true? So basically that reduces down to deciding whether the observation is in the body or the tail. So is the observation consistent with the idea that HO is true? So this will just be a yes or no question, yes or no answer. And yes would imply that the observation is in the body, and no would imply the observation is in the tail. Okay, so remember before we decided whether the observation was in the body or the tail by comparing test statistic to critical statistic, or comparing p-value to alpha. So in this case, let's go back here, and because this is only a right tail test, we only have to find chi-square critical on the right, where the right tail starts. So let's go ahead and find that. Remember, any critical statistic will come from a table. So we're going to use the chi-square table. We haven't looked at that in a while, so let me project that. so we're looking at the chi-square table. This would be page 563 in the book. So the way this table is laid out, recall, is that on the first column are the degrees of freedom, which would be n minus 1. And so our sample size n is 40. So we're going to go 40 minus 1, which is 39, and try to find exactly 39. And if 39 is not there, we'll pick the number in the chart that's closest to that. So the number closest to 39 will be 40. And then now we're going to go over to the correct column. And so notice these columns are labeled as area to the right of the critical value that we're trying to find. So
Confidence level of body is 0.95.
yeah, so we're trying to find where this right tail starts. So that has the chi-square value, and so the body is 95%. So we said that that one tail was 5%. So to use this table, we need to know the area to the right of this critical value that we're trying to find. So this critical value we're trying to find has a total right area of 5%. So we're gonna use 5%. So 5% will be here, and then we go down to the correct column. So it will be this column there, and we're going to go down to 40. So that looks like 55.758. Any questions? No? Okay. There's a fancy noise. Must be something up here. Alright, so this is chi-square critical that we're looking for. Somebody remind me what it is.
55.758.
Okay, so that's where this right tail starts. So just like before, we want to compare that to the test statistic for our observation. And so right now we don't know where it is in the picture, but I'm just going to draw it somewhere in the body for now. So that's our observation. It'll have a chi-square test. And just like before, any test statistic will come from a formula. So let me give you that formula now. So the formula for chi-square test will be this formula, n minus 1 the quantity times s squared over sigma squared. So let's go ahead and calculate chi-square test for this example, given the observation of our sample. So n will be
39.
Yeah, it'll be 40 minus 1, which is 39. S is the sample standard deviation that's given. And then sigma. Okay, very good. So remember, sigma is a population measurement. So we actually don't know that because we have only observed the sample measurement. But there's a step in hypothesis testing, we're assuming HO is true, so we're assuming that sigma is 0.1. So go ahead and punch that in, that's not what we get.
Fourteen point oh four.
14.04, so chi-square test is 14.04. So 14.04 is to the left of the critical chi-square value 55.758. So originally how it was drawn, to the left of the critical value was correct, so we don't have to redraw that. So again, the critical value defines where the right tail starts, and everything to the right is in the right tail. But ours is to the left, so therefore we can't be in that right tail. So therefore this observation is in the body of the distribution, not the tail. Any questions? So one thing I want to point out to you guys is if you look at how chi-square test is calculated, basically you have an s squared here divided by a sigma squared. And can a number squared ever be negative?
No.
No, good. So if you have s squared, which is always positive, divided by another number that's always positive, then this ratio will always be positive. And then you're multiplying by n minus 1, so can n minus 1 ever be negative?
No.
Yeah, good. So n is the sample size, the number of people you're observing. So n always has to be a number bigger than 1, or bigger than 0. So even if it's 1, for one person in the sample, then this will be 0, so you can never have a negative number. So the smallest value of this chi-square can only be 0. So this distribution actually goes from 0 to positive values. Okay, so we've determined that this observation is in the body of the distribution. So then we're going to go on to step 3 and answer the question of, is the observation consistent with this idea that HO is true? And because it's in the body, we say yes, the observation is consistent. So if we have one observation that's consistent with an idea pertaining to all observations, what conclusion can we make about this idea if only one observation so far has been consistent with it?
Fail to reject.
Yeah, very good. So we can't just accept the idea for all possible observations. The best we can do is not throw it out or fail to reject the idea. And the idea under consideration here is HO. So we fail to reject HO. And remember, fail to reject doesn't mean accept, but you can think of it as leaning towards accepting. So we're leaning towards accepting HO. And what can we say about H1?
Fail to accept.
Yeah, fail to accept. Again, fail to accept doesn't mean reject, but we're going to lean towards rejecting H1. Good, so in this case, both these conclusions are true, but we always want to bring it back to the original claim. So the original claim here was HO or H1? Yeah, so look at step 1 of hypothesis testing that we just did. So the original claim we labeled as HO, so then we go to see what we said about HO, which is fail to reject HO, so in this case, we fail to reject the claim. So we're leaning towards accepting the claim, but it's still a weak, wishy-washy conclusion. Any questions? Okay, And just as a review, if the observation had been in the tail, and which means that no, the observation is not consistent with this idea, then what can you say about HO?
Needs to reject.
Yeah, you cannot write, we reject HO, because you only need, one counterexample to show that HO is not true for all cases. Or at least the number of cases corresponding to your confidence level, 95%. So if you can reject HO,
You can accept H1.
you can accept it. Alright, any questions? So this is an example of hypothesis testing where your claim involved a population standard deviation or variance. So the reason we say one or the other is you can always convert from one to the other. So if your claim has a population standard deviation and you're interested in the variance, then all you do is square. And vice versa. If you start with the variance and you're interested in the standard deviation, you just take the square root. So here, our claim involved population standard deviation. And so the general steps of hypothesis testing were exactly the same as before, same exact framework. The only difference is in step 2 here, when we go to assume HO is true and we draw the distribution, because we're dealing with a measure of variation, the distribution is now a chi-square distribution. And because it's a chi-square distribution, it'll have a critical statistic that corresponds to a chi-square critical. And any critical statistic we find from a table, so we use the table to locate an area to the right that needed to be 5% because our confidence level was given at 95%. So that means there needs to be a total tail area of 5%. And because we're dealing with one tail, because we have H1 being only one inequality, we have a one tail test, and it's a right tail test. So this right tail has to be the full amount of alpha, which is 5%. So then we use the table to look up a right area of 5%, and the table gives us this critical chi-square value. And so once we get the critical statistic using the table, we use a formula to find the critical, we use a formula to find the test statistic. So the formula, that'll be in your book and on your formula sheets, is this formula for chi-square test. And all we do is plug in the numbers that we observed in the sample directly. And we got this number 14.04. And then we just compared these two measurements, just like with all the other hypothesis testing we did. Compare the critical statistic to the test statistic. And here we determined that the observation was in the body, and then we go to make the appropriate conclusion because it's in the body. Okay, any questions? All right, so now that we talked about hypothesis tests that involve a claim that has a standard deviation, let's now talk about the next variation, the next variety, which is hypothesis tests that have a claim that involve two population proportions. So again, this will be a hypothesis test having a claim with two population proportions. So this will be section 9.1. So, if you remember, the three types of hypothesis tests, the three types of claims that we did before, all had to do with claims involving one proportion, or one population. So, recall that when we talked about claims involving a proportion, that claim had to do with a proportion for only one population. So for example, if we wanted to know, if you have a particular website that you happen to administer, for example, and you happen to know that it's a pretty popular website, your claim might be that at least 60% of the world uses this website. So the world is your population, and there's only one population involved. Or when we did a claim involving a mean, we did the example of a mean IQ for this new country that you're visiting. So the average IQ for everybody in this new country you're visiting, that has to do with one population. And so we're dealing with this measurement for that one population. Or the one we just did with a standard deviation for the entire factory. That entire factory was the one population. So all the cases we've done so far were measurements involving one population of interest. So now we're going to do two populations and talk about one that would apply. So let's put this in the context of an example. So let's say that you're interested in knowing whether a drug is effective in doing what it claims. So let's say that your claim is that the drug is effective. And let's say P is the proportion of success for everybody who takes the drug. So P here, let's say is so every single person who takes the drug, you want to know what's the proportion of success. And let's say success is whatever it is the drug purports to do. Like, let's say the drug says that it lowers cholesterol. So P here would be the proportion of success or proportion of people who get their cholesterol lowered for everybody who takes the drug. So in this case, we would have one population, which is all drug takers. And we want to know the proportion of people who get their cholesterol lowered in that group of everyone who takes the drug. So this is only one population of interest. Now, if the drug is actually effective, do you know what the true proportion of success should be for all drug takers?
For that sample.
Yeah, remember any claim has to do with the population. Yeah, so you're right. The only thing that you can observe is the sample itself. But any claim in any hypothesis test has to do with a population statement. So in this case, if your statement is that the drug is effective, do you know what the true P, or proportion of success, should be for everybody who takes the drug?
If you're claiming the drug is effective, you'd say 100%, so all of
Okay, very good. So it depends on what you mean by effective, right? And you know in real life, just because something is effective doesn't mean it occurs every single time, right? You can say that gravity works and it's an effective idea, but you don't see things falling all around us, right? So just because something is correct or effective doesn't mean that you should be able to observe it 100% of the time. So now the question is, if we say that something works or this drug is effective, what should this true number be?
Well, I mean, that, in its own way, that's like saying you're putting a confidence interval into it. You're saying that it'll have this much success with this much error based on however many trials.
Okay. So again, it depends on what you mean by effective, and people have different standards for effectiveness. So oftentimes you don't know what that standard should be. You don't know what the ground truth should be. But the most effective way of comparing this is to compare it with everybody who doesn't take the drug, and then if that difference is big enough, then you say that the drug is effective. So instead of just assigning this proportion of success for what success should be, like 100% or 90% or whatever arbitrary number you use, instead of just taking one population of all drug users and assigning what that proportion of success should be for that one population, we're not gonna look at two populations, where one is the drug using group and the other is what we call a control group, which is everybody who hasn't used the drug. And so, now we're gonna use two different symbols. So P1 is the proportion of success for all drug users, and P2 will be the proportion of success for everybody who doesn't use the drug. So our claim then is going to compare these two different population successes. So now we have an instance where we have two populations involved and not just one. So if the claim is actually true and the drug is effective, then what do you think the relationship should be between P1 and P2? P1 is the drug group, P2 is the non-drug group. And you're measuring the proportion of success in each group. So if the drug is actually effective, then what should the relationship be between these two?
P one is greater than P two.
Yeah, P1 should be greater than P2. So now we can use these two populations in our claim, instead of just one population. Okay, so these are the statements for the claim that involve population statements. But then remember, we make the conclusion for this claim based on an observation with one or more samples. So our observation then will, instead of one sample to test one population like before, all the other examples, now we're gonna have two samples. So one sample will be the drug group. And the other, so let's call this sample 1. The other sample will be sample 2, which we call the control group. So as a whole, everything should be the same, except for that one issue of using the drug or not. So in these two different samples, let's say that the sample sizes are the same. But because we have two different samples, let's differentiate between them by using different subscripts. So in sample 1, we're going to use a subscript of 1 for each of those variables. So the sample size of group 1 will be N1, sample size of group 2 will be N2. And so let's say that then you measure the number of successes in both groups. So for the 100 people in the drug group, let's say that you measure a number of successes that is, let's see. Let's say 60 people. So on its own, you don't necessarily know whether 60 out of 100 successes is considered good enough until you actually measure it to a group that hasn't ever used the drug before. So let's say we compare it to this control group where the number of successes, let's say is 5. So that means not doing anything, not taking any drug, 5 people get their cholesterol lowered out of 100 people. But taking the drug, 60 people get their cholesterol lowered. So the question is, intuitively, do you think this is a big enough difference for you to say that the drug is doing something versus maybe this difference could be caused by random chance? So you think it's random chance, or do you think this difference is actually big enough?
I think the difference is big enough.
Yeah, it looks like the difference is way big enough because the 60 is 12 times as big as the 5. So that's not just accidental variation. So intuitively, we should be able to conclude that the drug is effective just by looking at the sample, and that the claim is true and the drug is actually working. But in real life, the numbers aren't usually this dramatic, so we'll have to use hypothesis testing to conclude whether this difference is caused by natural variation, or if there's a true difference that the underlying distribution can't explain. Okay, so we're gonna go through with hypothesis testing. So the formal steps will be the same. The only difference is when we get to step 2 here, the underlying distribution might look like a different distribution, a different shape. And the way that we calculate the test statistic, the formula that we use will be different, and the table that we use to find the critical statistic will be different. But other than that, everything else will be the same. Okay, so let's go through the steps together. So we started with a claim, and we have an observation of now 2 samples instead of 1 to try to make a conclusion about that population claim. So what should step 1 be?
Mathematically formulate your hypothesis and counterclaim?
Yeah, so identify the 2 statements, HO and H1. So to identify those 2 statements, first step is to generate the second statement to begin with from the claim. So that would be the counterclaim. So the counterclaim is just the opposite statement. What's the opposite statement to the drug is effective?
It would be P1 is less than or equal to P2.
Okay, very good. So the drug is not effective. So that's our statement in words. That's our counterclaim in words. But now we convert that English statement in words into a mathematical statement. So to say that the drug is not effective means that either P1 could be less than P2, or the proportion of people who get their cholesterol lowered after taking the drug is even less than not doing anything and being in the control group. Or if P1 ends up being equal to P2, then that also means the drug is not effective, because it's the same as doing nothing. So in the counterclaim, either one of these could be true, and we can simplify this as just saying P1 is less than or equal to P2. So now that we have the 2 mathematical statements, we're ready to identify the null hypothesis. So recall the null hypothesis is the statement that has the equal sign. So which one is that?
The counterclaim.
Yeah, the counterclaim. So this counterclaim will be HO. And the other one will be H1. That was step 1 of hypothesis testing. Step 2 is assume that HO is true. And we're going to assume that P1 really does equal P2. Remember, in the null hypothesis, we're going to strip everything away except for the equal sign. So null hypothesis becomes P1 equals P2. So in step 2, we assume that HO is true, which means that we assume P1 equals P2. What is it?
I'm trying to wrap my head around that.
Okay. Do you need anything clarified?
I'm sure we're gonna get there, but you get 2 different, you get, your proportion of success for each side is different, right? But
Yeah.
here's the statement, so it's not like I can magically work one equation that's going to give me an answer on that, so like, how do we sort this out?
Okay, very good, very good. So great point. So the point was before, the whole reason we chose the null hypothesis having an equal statement was because that equal statement equals a number on the other side. But now you have 2 variables equaling each other. You don't have them equaling a number. So it turns out that really, when you're saying that P1 equals P2, really we do have a number on the right, and we're saying that P1 minus P2 equals 0. So our actual variable is P1 minus P2.
I did not sleep well enough for this.
I'm too sober for this.
I didn't sleep very well either after teaching.
Fair enough.
Alright. This is a subtlety though, being raised by a very good point, but the subtlety is that, now, when we look at the distribution, the variable involved, instead of just one variable, it's one variable that's represented by this expression, P1 minus P2. So, now we're gonna look at the underlying distribution. And our variable will be based on sample observations. So remember, the very first thing we did in hypothesis testing was we observed a number of successes out of another number of trials in the sample. So really we're observing sample proportions of successes. That was the one variable we were observing, the very first thing we did with hypothesis testing. But in this case, we're observing the difference between two proportions of successes. So this is a technicality that's true, but don't get bogged down in this. This isn't something that you need to really focus on. But the reason I bring it up is because when we were doing one sample proportion of success, what did the underlying distribution end up being?
Depending on what we're talking about, but in most cases, bell curve.
Yeah, it was a binomial distribution because it was a number of successes out of another number of trials in the sample, and it was a binomial distribution that you could fit with a bell curve. So if you have a sample proportion success, that distribution is a bell curve. If you have a difference between two sample proportion of successes, it turns out that that's also a bell curve. So the only reason why this part, this technicality is important is to help you remember that one proportion sample is a bell curve, so a difference between two sample proportions is also a bell curve. So you have a bell curve. And if this is really true, you assume that HO is true and P1 really does equal P2, then this most commonly appearing value, where the peak is,
Would be 0.
yeah, it'll end up being that P1 equals P2, and that will end up being 0. Okay, so good. So that's another technicality that is meant to add enrichment, but don't get bogged down on that. So the only important thing is the consistency between this and what we've already talked about, is that ultimately this is gonna have a certain area for the body and a certain area for the tail. So how much, let's say that the confidence level is 99%. So again, that's gonna be given. So that means that the area of the body is 99%, and any tails will add up to the remainder, which is 1%. So is this a one-tail test or a two-tail test? Well, this is kind of a tricky question. Just because there's two variables doesn't mean it's a two-tail test.
H1 is only one tail.
Yeah, good. So whether it's one tail or two tails depends on the number of inequalities, not the number of variables. So you always look at H1, and H1 in this case turned out to be the claim, which is P1 is greater than P2. So there's only one inequality here, so this is a one-tail test. So if it had been P1 is greater than P2 or P1 is less than P2, that would have been a two-tail test. But this is one tail, and for these two variables, the way you tell is keep the variable with the subscript of 1 on the left and the variable with the subscript of 2 on the right, like it is here, and then look at the sign of the inequality. So here the sign of the inequality is greater than, so this will be a right tail test.
So they have to be numerically in order with the inequality sign. So if for whatever reason this was the other way around, we would have to swap it around so that it would actually factor out numerically where it is
Yes,
numeric one, whatever the sign is supposed to be, and numeric two.
yes, so remember, what we just said before was that subscript 1 was on the left, subscript 2 was on the right. That seems like a really arbitrary thing. So the reason for that is because the variable we're keeping track of is this difference, P1 minus P2. And really what you're doing is, from algebra, you're just moving this P2 over. So P1 minus P2 is greater than 0. So all we care about is this variable, P1 minus P2, and then whether it's greater than or less than 0. Because it's greater than, it's to the right. So these are two different ways of explaining the same thing. It's a right tail test. Okay. So once we establish that this greater than inequality means it's a right tail test, now we're ready to label the size of the tails. So all the tails, no matter what distribution it is, remember, add up to alpha. In this case, the confidence level is 99%. Alpha is always what's left over from 100%. So alpha is 1% or 0.01. And then all the tails add up to that alpha. So in this case, there's only one tail, so that one tail is the full amount of alpha.
And since we're using proportion, this is all gonna be z's, right?
Yeah, since we're dealing with variables that have to do with proportion of successes, this is all z-score. So z critical here.
2.575.
So we want to be careful. We want to find the z-score that has a left area of 99%. Your table is going to have a section where there's a main table here, and there's like this little peripheral table down at the bottom. And you want to be careful because the main table lists the z-scores along with their left areas. But this little extra table here lists the z-scores along with their middle areas. So as long as you're clear on that, you can use any of the two tables, but you have to realize that the convention of these two tables are actually different. So if you know the left area, for example, this left area relative to the z-score you're trying to find should have a total left area of how much?
The entire other part of that should be 99%.
Yeah, the entire left area under the bell curve should be 99%, left over from 1%. So this left area you're looking for is 0.99, and then you want to find the corresponding z-score. Versus over here, this convention is a middle area. So a middle area means that if you had this another left tail here, then this boundary here would be found using this middle area. So if you had 1% over here, that means that there's another tail here of 1%, even though this is a one-tailed test. But this middle area would be how much if both sides were each 1%?
It'd be 98.
Yeah, so 98. So then to get the same answer using this bottom table here requires looking at 0.98 as a middle area.
Which is 9.
Which is a 9, right? So if you look at 0.99 as a left area, then you'll see that it should be 2.33. So 2.3 here, and then add an extra 0.03. You guys see that? So find the number that is closest to 0.99 representing the left area.
Oh no,
Oh, okay.
that part makes sense, but normally when we talked about tails, when we said we're doing a confidence level of 99%, we would end up splitting that on either end, where the middle is still 99%. So now it feels like we're changing how we did this.
Okay.
So we normally have the alpha divided by 2, right?
Right. So let's, because I was explaining the difference between these two tables that are in your Z-score chart, let's look at another example, maybe that'll clear it up a little bit more. So let's say that so to avoid confusion, let's say that we're dealing with two tails, but this explanation will be able to generalize whether you have one tail or two tails. But let's say, for the sake of example, you have two tails here, and you have this middle area as, let's say 95%. So let's say that you're trying to find this right boundary here. So if you use the main chart in the Z-score table, then that requires a left area in order to find it. So what's the total area to the left if this middle area needs to be 95%? So that means both tails combined add up to 5%, each tail is 2.5%. So the middle plus 95 plus 2.5 is 97.5%. So it's this total left area is 97.5%. So if you're going to use the main table in the Z-score chart, then we're going to look up 0.975 as a left area, because that represents a left area. So that should be 1.96. Right?
For 9.7,
For 0.975 as a left area.
no, because that's just 95. 2.7, you said 9.75 should come up to 9.75. No, you're right, it's 1.96.
Okay. So it's 1.96. And that's how you got the answer, by using the main part of the Z-score table and looking up the left area. But if you use that tiny little table on the right with only like 3 numbers in it, then that requires a middle area. So if you look at this picture, this boundary that we had, the total left area was the 97.5%, but the total middle area here is how much?
That's 95.
Yeah, it's 95. So if you use this little side chart here, then you would look up a middle area of 0.95, and you'll get the exact same answer, 1.96. So the convention of this main chart is left area with Z-score. The convention of the other chart is middle area. Yeah. Any questions? So when in doubt, use the main chart and use the left areas. And also, the main chart has a lot more values. The middle area only has like the 3 columns. Okay. So where were we? So we were trying to make a conclusion regarding this claim, the drug is effective or not, and then we went on to step 2. And said that assume the null hypothesis is true. So we found Z critical here. And what did Z critical turn out to be?
2.33.
Yeah, 2.33. So that's where the right tail starts. Everything inside that right tail will be in the tail area. So then ultimately we want to decide whether the observation is in the body or the tail, and that'll have its own test statistic. In this case, it will be a Z-test, and any test statistic will come from a formula. So I'll give you the formula right now. Yeah. So that's the formula. So the formula z-test involving two population proportions will be p1 hat minus p2 hat. So the first time you see this, it'll be hideous. But after that, maybe it won't be so bad. And then divide by the square root. I'll write it first and then I'll describe what the symbols are. Okay, so this is the formula for z-test for two population proportions. So this is there's a fraction where the numerator is p1 hat minus p2 hat minus the quantity p1 minus p2 divided by the square root of, so you notice that this is a p with a symbol over it, but it's not a hat. It's just a horizontal line, so we call it a dash. So this is p dash, and I'll explain what that means in a moment. So p dash times q dash divided by n1 plus p dash q dash divided by n2. So let's talk about what these symbols mean. So first of all, anytime you see a hat, you know that that's a sample variable. So p1 hat is the proportion of success in sample 1. So in this case, sample 1 is the drug sample. And remember, it's a proportion of success. So right now we have a number of successes, which is 60. So what would the proportion of successes be? Yeah, 60 divided by 100, the sample size. So that will be 0.6. So p hat will be 0.6 minus, what's p2 hat?
120.
Yeah, 5 divided by 100. So 5 successes out of the total 100. So it'll be 0.05. Maybe it'll be easier if we just let me start. Okay, so the next symbols are P1. And notice P1 is the population proportion of success for group 1. And group 1 is everybody who takes the drug. So this is the proportion of success for everybody in the world who uses the drug. But we don't know that. We only know the proportion of success in the sample that we observed taking the drug, 100 people. So how do we find this number? The proportion of success is out of everyone who uses the drug in the whole world. So we actually don't know that, right? And likewise, we need to know P2, which we don't know, so same reasoning. Proportion of success in everybody in the world who doesn't use the drug.
But wouldn't that come back from where we're plugging in numbers over here to get those scores and areas?
Okay, very good. So we don't know these individual numbers, and anytime we're dealing with population variables, we don't know them. But remember, in hypothesis testing, in step 2, we always make an assumption about the population variables. So here we're assuming that P1 equals P2. So even though we don't know them individually, this difference should be what if P1 equals P2?
0.
Should be 0, very good. So if two numbers are identical and you subtract them from each other, they're always 0. So this difference is 0. So when you're dealing with a situation, hypothesis claim with two population proportions, the formula for z-test, this second part of the numerator will always be 0. Now, why doesn't your book just ignore that? That's a good question. But the reason, I'm guessing, that they leave it in is so that you can see the patterns and the consistency with all the other test statistics. So all the other test statistics, you always have an observed value, x, for example, minus the mean. So it turns out the mean just happens to be 0 here, divided by the standard deviation. So it's just consistent with all the other test statistics that you've seen. So it's the same structure. So data point minus mean divided by standard deviation. The mean just happens to be 0 here. So now let's talk about these other variables down here. Let's do the ones that we know immediately. So N1 is a sample size for group 1, which is
100,
100,
and two is also 100.
and 2 is also 100. So this tells you that the sample sizes don't necessarily have to be the same. One could be 100, one could be 120, and so forth. So now let's talk about what P dash and Q dash means. So originally, we have two different samples, sample 1 and sample 2. What P dash means, it refers to the pooled proportion of success, which means if you were to combine both of these samples into one pool, what would the proportion of success be for that new pool? So a proportion of success is simply the number of successes in that group divided by the total number. So in this case, what's the new number of successes if you were to combine everything into one pool?
65 at 200.
Yep. So add the x's and then add the n's and then divide them. So it'll be 65 divided by 200.
0.325.
Yep. 0.325. So again, this is the proportion of success if you were to combine both these individual samples into one pool.
Well, that's half of this thing, that's not all of it, because your Q is basically the part that wasn't, and we need to do that too.
Yeah, very good. So that's P dash,
But
and then
if you
Q
got
dash.
that one should be the same, just subtract it from 1, so 1 minus 0.325 should be 1.
Very good. So Q dash is always calculated as 1 minus P dash. So that would be 0.675. So again, that's Q dash is 1 minus P dash. And so P dash, for example, is the pool proportion of success in the entire new pool. Notice that it's not the same as adding up the two individual proportion of successes, because P1 hat, the proportion of success in just sample 1 is 0.6, and P2 hat, the proportion of success in just sample 2 is 0.05, 5 divided by 100. But if you added these up, that's not the same answer as the pool proportion of success, which is 0.325. So you can't just add up these two to get 0.65.
Now, I see how we work the body under that, but when you've got, you know, your answer is gonna basically equal 1, so, I mean, are we multiplying 0.325 and 0.675 and then taking the square root?
Yeah, so we're multiplying these two numbers together, dividing by n1, and then adding it to the next quantity, whatever that is, then taking the square root.
So they're already pulled, so you have to figure that out anyway and then put it together that way. Okay, that checks. Kinda like alpha divided by 2. Alright.
Yep. So in this case, P dash is 0.325. So we'll do that substitution. Q dash is 0.675. Multiply those two, divide by 100, and then add it to the next one. In this case, the two terms happen to be exactly the same because n1 is equal to n2, but that's not necessarily generally always the case. So go ahead and punch this in, and let's see if we get the same answer. So it should be higher. Sure.
8.3.
Okay, that sounds right. Anybody else getting that? Okay, sounds like it's 8.3, but if you need help punching it in, I can help you after class. So, everybody else getting 8.3? Okay. So, let's say that z-test is 8.3, that sounds right. So, we already did step 2, which is properly identifying the size of the bodies and the tails. So now we're on step 3, which is incorporating the observation in. So a z-score of 8.3 for our observation has to be to the left or right of 2.33.
To be in the body, it has to be to the left.
Well, a z-test is 8.3, and there's only one tail, a right tail, where it starts is 2.33. So our observation is the number 8 to the left or right to the number 3.
It's to the right.
It's to the right, right? So it's to the right of where the right tail starts, so therefore it has to be in the right tail. And in this case, it happens to be pretty far to the right. So the most important thing about this picture is, first of all, knowing that it's a bell curve, because we're dealing with a claim that has proportions in it. In this case, 2 proportions, but one proportion will be a bell curve as well. So claims with proportions will be a bell curve. And then the confidence level gives you the area of the body. This should be 99%. We talked about a tangent and changed this. So this is 99%. That's the area of the body that's equivalent to the confidence level that's given. Confidence level that's given, I erased it, it was 99%. And then that leaves alpha, 1%, that's distributed across all the tails. There's only one tail here because of H1. We said that H1 was that P1 is strictly greater than P2. So one inequality, one tail. It's greater than, so it's to the right. So the most important thing in this picture is knowing that it's a bell curve, identifying the confidence level pertaining to the body, identifying the area in the tails, labeling where the tail starts, that's Z critical, and then Z test, we know has to be the right of 2 because it's 8 here. calculated from this formula, 8.3. So this is the most important part of the picture, is to realize that the observation is inside the tail of the distribution. So once we realize it's in the tail, then we're ready to answer this question, is the observation consistent with the idea that HO is true? So because it's in the tail, no, it's not consistent. So if we already have one observation that is not consistent with an idea, then we can say that the idea is not true for all cases. So you can reject HO, you can accept H1.
Which means the drug is effective.
Yeah, very good. So then we bring it back to the original claim, and the claim happens to be H1. So because we end up accepting H1, we accept the claim. So we accept the claim that the drug is effective, and this is consistent with our intuition, where if we had observed the sample, we would have seen that this difference between 60% effectiveness taking the drug versus 5% effectiveness, that's a huge enough difference for us to say that that's not caused by chance. It's caused by an actual difference in taking the drug. And the final conclusion is consistent with that. So this is an example of a hypothesis test with a claim that involves two population proportions. It turns out to be a bell curve. Z critical you find the same way that we found Z critical with any bell curve. And then the only difference is the way we calculate Z test is through this kind of ugly formula. But the formula will be available to you in your book and your notes on the test. Any questions? All right, that's it for today. Have a good day, have a good weekend, guys.
So we do 95%,
That's the middle area of 95%,
so.
which is the same as the left area of 97.5%.
That's why I was wondering about when we did that particular example, yeah, maybe that's just correct. I see, so we have 199, I know I'm not doing this part wrong, but I figured I had actually put the whole thing. Do the rest of it, okay, then I. Trying to.
Yeah, sounds like you're right.
I don't know, because, you know what's really helped me, like the people on Khan Academy, and you watch them